Welcome to today's class on functional analysis. Today we discuss condition for a product space to become a Banach space. So we state a theorem. Theorem 8.2b. Let x1, x2, etc. xm be normed spaces. And x equal to x1 cross x2 cross etc. cross xm. Then x1, x2, etc. xm are all Banach spaces if and only if X is a Banach space in one of the norms P norm given by 5.2c. For definition of norm, you can refer 5.2c. Now we prove this. Proof: let x1, x2, etc. xm be Banach spaces. If xn is a Cauchy sequence in x is equal to x1 cross x2 cross etc. cross xm, then xnj is a Cauchy sequence in xj for j is equal to 1, 2, etc. m. Now you know that xj is a Banach space, so you let xn of j converges to x of j in xj for j is equal to 1, 2, etc. m. Then by 5.2c xn converges to x, where x is x of 1, x of 2, etc. x of m in x. So you have a Cauchy sequence in x, and now you have converges in x, therefore x is a Banach space. Conversely, assume that x equal to x1 cross x2 cross etc. cross xm is a Banach space. Fix j 1 less than or equal to j less than or equal to m. Let xn j be a Cauchy sequence in xj. let xn equal to 0, 0, etc. 0, xn of j 0, etc. 0 belongs to x. Clearly, xn is a Cauchy sequence in x. You know that x is a Banach space, so let xn converges to x in x. Then by 5.2c, xn of j converges to x of j in xj. Hence, xj is a Banach space for j is equal to 1, 2, etc. m. So that's this theorem. Now we discuss condition for space of bounded linear maps to become Banach spaces. So we state a theorem 8.2c. Let x and y be normed spaces and x not equal to singleton 0. Then BL of xy is a Banach space in the operator norm if and only if y is a Banach space. So prove this theorem. Proof. First assume that y be a Banach space. Let y be a Banach space. When you consider a Cauchy sequence in BL of xy, we are going to show that it is convergent. So let Fn be a Cauchy sequence in BL of xy. For every epsilon positive, there is a positive integer n naught such that the norm of Fn of x minus Fm of x less than or equal to norm Fn minus Fm into norm x. This is less than epsilon times norm x, since Fn is Cauchy. For all x in x, n m greater than or equal to n naught. Hence, for every fixed x in x, sequence Fn of x is a Cauchy sequence in y. Therefore, Fn of x converges in y since y is Banach. Y is a Banach space. Let Fn of x converges to f of x in y. We have f from x to y is linear. and letting m tends to infinity in norm of fn of x minus fm of x less than or equal to epsilon times norm x, we have norm of fn of x minus f of x less than or equal to epsilon times norm x. This is because fn converges to f. It's true for all x in x and all n greater than or equal to n naught. That is fn minus f belongs to BL of xy. And since f equal to f minus fn plus fn, we have f minus fn belongs to BL of xy and fn belongs to BL of xy. We see that f belongs to BL of xy. And norm fn minus f converges to 0 as n tends to infinity. That is, sequence fn converges to f in BL of xy. Therefore, BL of xy is a Banach space. Conversely, let x not equal to singleton 0 and BL of xy be a Banach space. Consider a belongs to x, a not equal to 0. Therefore, by 7.10a, there is some f in x dual with f of a equal to norm a not equal to 0 and norm f equal to 1. So consider a Cauchy sequence yn in y. We are going to show that this is convergent and define fn of x equal to f of x into yn for x belongs to x. Then fn belongs to BL of xy. And norm of fn minus fm, this is equal to norm of f into norm of yn minus ym. This is equal to norm yn minus ym because norm f is 1 for all n m equal to 1, 2, etc. This fn is a Cauchy sequence. As fn is a Cauchy sequence in BL of xy and BL of xy is a Banach space. So let fn converges to f in BL of xy. We have fn of a is f of a into yn. So that this implies yn equal to fn of a by f of a. So this is equal to fn of a by norm a because f of a is norm a, and this converges to f of a by norm a. since Fn converges to F. This is in Y. That is, the sequence Yn converges in Y. So you have started with a Cauchy sequence in Y, and now we have it converges in Y. Therefore, Y is a Banach space. Now we are going to prove that the dual space of every normed space X is a Banach space. Theorem 8.2d. The dual X dual of every normed space X is a Banach space. Proof. Let X be a normed space. Then X dual is actually BL of XK. Therefore, by 8.2c, BL of XK is a Banach space, since K is a Banach space. Therefore, X dual is a Banach space.